Hello there and welcome to this series of videos going through the content of A-Level Maths. Here we're looking at moments and resolving forces so we can answer questions from exercise 7D. So when I think of moments, I think of that balancing beam that we had. Generally had two pivots underneath it, reaction forces at both those pivots, and we had to put weights at different points on the rod, and then we worked out balancing forces, and upwards forces equals downwards forces. So we're going to go back to that topic there, but this time our rod is going to be at an angle. So remember, the way we take a moment, or the formula for taking a moment, is distance times force, and the force has to be applied in the perpendicular direction to the rod. Okay, so that's going to be important later on. Let's crack on with this question here then. So a uniform rod of length AB has a mass 40 kilograms and a length 10 meters, rests with end A on a rough horizontal ground. So there is friction on this ground here. The rod rests against a smooth peg C, and A to C is 8 meters. The rod is in limiting equilibrium at an angle of 15 degrees to the horizontal. So the rod is about to slide from its resting point that's on this peg here. Calculate the magnitude of the reaction at C. So that's going to be C is at this peg here. So drawing a diagram to label all the forces, the weight, the normal reaction, the friction, and split the components if needed. So this is our reaction force between the rod and the ground. This here is our reaction force between the rod and the peg. And then this force here is the centre of mass force, centre of weight force. That's going to be the 40G force there for the weight of the rod. So we've got to work out the reaction at C, so we're going to work out this S force here. The rod will have a tendency to slide downwards with the base moving to the left, hence friction will oppose this. So that's why we need a friction force acting to the right, because if you can imagine placing a pencil and then putting a peg in at a point on a wall, that pencil could potentially slip down the peg and end up lying flat on the ground. So, what we're going to do next is we're now going to resolve this 40G Newton force here, because you can see at the moment that if we were to tilt our head slightly and look at this and pretend that this is the horizontal, that this 40G force here would not be acting in the correct direction. At the moment it's not perpendicular to the rod, so that's why we need to resolve forces here. So we need to identify that the force that we're actually going to be working with on the 40G force is 40G cos 15. That is the perpendicular force, so when we work out moments, that's the force we're going to use. And we'll have obviously 40G sine 15 going down the slope. Put in your lengths, they're important because it's going to be moment equals force times distance. So we're going to work out S now. So taking a moment about A, it's generally a good idea to take a moment about A because you're going to have your reaction force to the ground here and your friction force here, and it'd be better if our equation did not have these two unknowns in it. So to make sure that we don't have these two unknowns in our moment equation, we take a moment from this point, and therefore these distances here are going to be 0. So therefore we're going to take a moment about this point A here, and then remember it's going to be moment equals distance divided by, times by force. So we're going to look at this force first here, 5 meters in distance and a force of 40G cos 15. Notice here how we're not using just the bog standard 40G, we've had to resolve it so that the distance is perpendicular to the moment, to the force. So what we're going to do then is we're going to work out which direction this is now travelling. Will it appear on the left hand side of my equation or the right hand side of my equation? Well, if I imagine a clock face at point A and it's going to be going down on the right hand side, that's going to be a clockwise moment for this force here. So it's going to be on the left hand side 40G cos 15, that's the force, times the distance of 5. So 40G cos 15 times by 5. And then on the other side, the only other force we have is this S force here at a distance 8 meters away, and this is perfectly at a right angle to the rod, so no resolving needed for this force, equals 8S. So divide both sides by 8, and we get 25g cos 15, work this out numerically, and we get 237 newtons as our value for S. Now, what's happened to this 40g sine 15 force here? Well, in this case, we do not include it as a moment for A. This is because it actually acts down the rod through the point A, so we effectively say that this has a distance 0 from the rod, from the point that we're taking a moment from, so it basically can be ignored. We're only taking forces that are perpendicular to the rod. Any forces that are parallel to the rod, we kind of just ignore them. Moving on to part B then, the coefficient of friction between the ground and the rod, and that's where these two forces here come into play. We've got the reaction force between the ground and the rod, and we've also got the friction force that's keeping the beam in equilibrium. It's on the point of moving, it's in limiting equilibrium, so it's going to be the maximum value of friction being applied here. So now you can resolve horizontally and vertically to find the remaining forces. So instead of resolving up the slope and perpendicular to the slope, we're actually going to change our focus now to being purely horizontal and purely vertical. So this 237 force here will need to be resolved itself. It's going to be an upwards force of 237 cos 15 and a horizontal force of 237 sine 15. And we're going to go back to the 40g force here and ignore that we've resolved this force here. Great. So, resolving horizontally then, so that's going to be from left to right. Leftwards forces must equal rightwards forces, and it must be the case then that F here and 237 sine 15 must therefore balance each other out. Resolving vertically now, we want upwards forces to equal downwards forces, so we want R plus 237 cos 15 to balance out with 40g. So R plus 237 cos 15 will balance out with or is equal to 40g. And now we can apply F equals mu R. So rearrange this to get R on its own. So we've now got what F is, we've now got what R is, and now we can just use F equals mu R to work out what mu needs to be. So friction is this F force here, 237 sine 15, that goes on the left. Then it's equals mu times the R force, which is 40g minus 237 cos 15. Divide that onto the other side, and then use your calculator to work out the answer, and you get 0.37 as your answer for the coefficient of friction. So there we are. So we've started on part A, where we were looking at just the perpendicular forces to the rod, and we took a moment about A. And then for part B, we changed our perspective and went back to horizontal and vertical forces, so that we could use F equals mu R. It's quite a good idea to take a pivot point from either end of the beam, in this case point A, because then the reaction force and the friction force kind of cancel each other out. Right, okay, so moving on to a different type of question here, where we have now a ladder of mass m kilograms, a length 3a, has one end A resting on a rough horizontal ground, the other end B rests against a smooth wall. So just notice here the difference in the terminology here. It's a smooth wall, so no friction on the wall, but a rough horizontal ground, so friction on the ground. If it was both rough, they'd both have friction. If it was both smooth, neither of them would have friction, but I doubt that would happen. A load of mass 2m is fixed on the ladder at point C, where the length from A to C is A. The ladder is modelled as a uniform rod, and the load is modelled as a particle. The ladder rests in limiting equilibrium at an angle of 60 degrees to the ground. Find the coefficient of friction between the ladder and the ground. So this is our scenario here. We have a ground and a wall. They will obviously meet at a right angle. 60 degrees to the horizontal. Halfway up that ladder will be the weight force of the ladder, that's mg. And we have the load at C, which is 2mg, that's the distance A away from A. So we now put in our reaction and our friction forces. We've put an Rg force here, that's standing for reaction force to the ground. And we also need a friction force down near the ground as well, because it is a rough horizontal ground. Now, which direction have we put this in? We've put it to the right because the ladder will potentially slip down the wall, which would mean that it slips leftwards on the ground, so friction will act in the opposite direction, and that will be to the right. The next thing we've got to do is put a reaction force at the wall. Now, we would put a friction force at the wall as well, but it does say it's a smooth vertical wall, so there's no friction going to be applied to the wall there. We've got a distance A here, 0.5A here, because it will be 1.5A in total, because the total length is 3A, so there we are, that's our full force diagram needed. So what we need to work out then is the coefficient of friction between the ladder and the ground. So we're going to use F equals ma on these two forces here, but we also don't know the mass of our ladder and of our extra particle here. So that means we have to do a little bit more extra work in working out this RW force here. I'll show you why that is at the end of the question. So the first thing we're going to be doing then is taking moments about A. Now, as we're taking moments about A, we're going to need to resolve some of these forces here so that the force is then perpendicular to the ladder. We're not just going to take the 2mg as a whole force, we're not going to take the mg as a whole force, we're just taking the amount of force that is perpendicular to the slope. So it's really important you're good at resolving for this part here. 2mg cos 60 here, mg cos 60 here, not interested in the forces going down the ladder. And we also have to resolve this RW force here. This could be RW sine 60, it could also be RW sine 30, so cos 30, depending upon how you look at the question. So we can now start to put our equation together. We're taking moments about A and we're saying clockwise moments equal to anti-clockwise moments. So the first moment we'll look at is this red moment here. Distance of A, force of 2mg cos 60 perpendicular to the ladder. So it's going to be on the left hand side here 2mg cos 60 times A. Why on the left hand side? Well, if you can imagine that A is the centre of our clock, it's going to be going downwards and to the right. That means it's definitely going to be going clockwise around that clock. The next force we're going to be considering them is the mg cos 60 force. It's a distance 1.5A away from the pivot point A, or the point I'm taking moments from, and that also will be going clockwise around our clock. So that will be mg cos 60 times 1.5A on the left hand side. The last force we need to resolve now is the RW sine 60 force. That's going to be going in the opposite direction, anti-clockwise around our clock. So that's going to be 3 times 3A times RW sine 60. So now that we've got an equation here, we can rearrange this, and we're looking to make RW the subject. We can cancel out A's, we can't cancel out M's, we can nearly cancel out M's. We can put these two together though, 2mg cos 60 and 1.5mg cos 60 equals 3RW sine 60. Make RW the subject of this equation here, and we can simplify this as well, finding out what cos 60 is, sine 60 is, and doing 3.5 divided by 3. And this here is our final value for RW, 7mg root 3 over 18. Okay, so now we need to work with some different strategies. We've taken moments about A, but we're still no closer really to finding the coefficient of friction between the ladder and the ground. So we'll now start to resolve horizontally and vertically. So that means the only force that we're going to take into consideration here are the RW, mg, 2mg, friction, and rg force. All of these resolving forces that we've just worked out are now null and void because we're just looking horizontally and vertically. We don't want to be looking diagonally now. So you kind of with these questions have to change your perspective from parallel and perpendicular to the slope to horizontal and vertical at this point now. So we're now going to resolve horizontally. So we're going to set leftwards forces equal to rightwards forces. So it must be the case that the frictional force is equal to Rw. Friction is acting to the right, Rw is acting to the left, no other forces are acting in that direction, so it's just these two forces must be equal to each other. So therefore we now know that friction is equal to 7mg root 3 over 18. So that's why we had to go and work out the RW force at the top there, because we want to work out the coefficient of friction. It'd be helpful if we knew the value of friction and the reaction force, and in doing that we needed to work out RW at the top there. Let's now resolve vertically, so we're just looking at upwards forces and setting them equal to downwards forces. So we're going to have Rg going upwards must equal 2mg downwards and mg downwards as well. Not the cos component of it, that's going at an angle, we're just looking horizontally and vertically, having changed our perspective now. So we've got here now that Rg is equal to 3mg, and now we can just do F equals mu r, and we know the value of F and we know the value of R. So now we can just do 1 divided by the other. Both of these terms here have m in them, so m's eventually cancel out. Super. And divide by 3, and g's also in both of them, so we can cancel g's out. So divide this by 3, and we get 7 root 3 over 18 equals 3 mu, and then dividing by the 3, we get 7 root 3 over 54. As a numerical value, that's equal to 0.22. Lovely, so there we are. That is a very standard question there, where we've got a ladder resting against a wall, and we're having to resolve forces here and work out moments. So it's kind of a really nice question in which they can ask you to A, resolve forces, and B, to do a moments question. Okay, your turn to have a go at this question here then. Pause the video and try this question out. Right then, let's have a go at this question then. So a uniform ladder, AB, of mass 20 kilograms, rests and sits A at the top of a smooth vertical wall and its base B on a rough horizontal ground. So before we read the rest of the question, let's draw our diagram. We're going to have a ladder. It's a smooth wall, so we're only going to have a reaction force at the wall here. It's a rough ground, so I'm going to have an Rg force here and a frictional force that's acting to the right, because my ladder potentially might slip down the wall, which would mean that the bottom will move to the left. And I also know it's a uniform ladder of mass 20 kilograms, and I know nothing else. So there we are. So I'll put that roughly in the centre there with a 20g force on it there. Great, the coefficient of friction between the ladder and the wall is 0.75, so I'll add that onto my diagram below there. A mass of 10 kilograms is attached to the ladder. Given that the ladder is about to slip, find the inclination of the ladder. Oh great, we've got to find the angle here, okay. When A is attached to point A. Now I remember from the question here that A is at the top of the smooth vertical wall, so I've got another force here that is 10g here. Great, okay, so now I need to work out this angle here then. So the first thing I'm probably going to try and do here is to now resolve all of my forces according to this theta angle here then. So theta's in there, and theta's in there. I'm going to have 20g cos theta here. I'm going to have 10g cos theta here. And I'm going to have RW sine theta here, because theta is actually on this side here, so it's opposite that side there. I don't know the length of my ladder, really helpful as well, so I'm going to refer to this as a length of 2L, where I have a length here L and a length here L. The reason I'm not setting the whole length equal to L is that I'll get fractions, so I'll just set my length of my ladder equal to 2L, and I'm sure that these L's will cancel out at some point. So, starting on part A then, what we're going to look to do is we're going to look to resolve from this point here, the point B that's at the bottom of the ladder. So taking moments about point B and setting clockwise moments equal to anti-clockwise moments. So the first two clockwise moments I'm going to have are 20g cos theta times L, and I'm also going to have 10g cos theta times 2L, because it's two lengths of that value L. And this will balance out with the force of RW sine theta times by 2L as well, and at this point now I'm going to cross out the L's. So my simplified equation here is going to be 20g cos theta. Oh, hold on, I could actually add these two together and make this now 40g cos theta will equal RW sine theta times 2. So if I divide by 2 and divide by the sine, I'm going to therefore get 20g times cot theta equals RW. Okay, so now that I've taken moments about my point B here, the next thing I need to do then is I need to, it's on limiting equilibrium, so F is equal to mu r perfectly, so I'm now going to resolve my forces horizontally and vertically and see where that takes me as well. So horizontally and vertically, therefore RW is equal to friction, so therefore friction is going to equal 20g cot theta. Then I'm going to have resolving forces upwards and downwards. So I'm going to have Rg as the only upwards force equal the two downwards forces, which are 20g and 10g, which will add up to a total of 30g. I can now use F equals mu r in my equation here, so I'm going to have friction, which is 20g cot theta, equal to mu, that's 0.75, times by r, which is 30g. Great, excellent. So what I'll do now is I'll move everything onto one side. I can cancel out the g's there. I can actually cancel out the zeros here as well, effectively cancelling out a factor of 10. So I'm now going to have 0.75. In fact, no, I'm going to do it the other way around. I'm going to multiply by tan onto this side, because that's how I'm going to find the angle, and then I'm going to divide by these two things here onto the other side. So I'm going to have here 2 divided by 0.75 times 3, so that's going to equal, on my calculator, 2 divided by 0.75 times 3, that's going to give me 8/9 equals tan theta, and now I can work out the value for theta, so inverse tan, answer, in degrees mode, 41.6. Lovely, so at the top of the ladder there we have a force, inclination of the ladder at 41.6 degrees. Right, okay, we're going to have to do pretty much the same working for part B then. So I think what's probably best off here is if we just completely start our diagram from scratch here. We've got point A at the top here with a reaction of the wall here. We've got a reaction on the ground here. We've got the frictional force acting this way here. Mu has not changed, it's still 0.75. We've got that 20g force acting downwards there of length L and L. We've also got that 10g force now in a different position now, not at the top of the wall, at the bottom of the wall down here. So doing exactly the same things as we did last time, the first thing we're going to need to do is to resolve our forces. So we're going to need this to now become 20g cos 60, and then this force here is now going to become RW sine theta. So let's get started in taking moments around point B down the bottom. We are going to have two forces only. We're going to have the moment of the force that is a length L distance away, and the force is 20g cos theta. So L times by 2g, so 20g cos theta. Now the 10g force here is not going to get involved because it's a distance 0 away from the point that I'm actually taking the moments from, point B, so that 10g force is not going to be involved this time. And then this force here is going to be a distance 2L away from my pivot point, and it's going to be a force of RW sine theta. So in this case I'll cancel out L's straight away. I can even cancel out 2's straight away, so it's now just 10, and divide by sine theta, so I'm going to get 10g cot theta equals RW. The next thing I needed to do then was to resolve horizontally. So you can see here there's kind of a pattern in how you're working with these types of questions. We're going to have Rw equal to friction, so therefore friction must be 10g cot theta. And then we're going to resolve vertically. So we're going to have here upwards forces equal downwards forces, and remember we're ignoring these resolved forces here. So we're going to have a 10g and another 20g, so that's 30g in total acting downwards. And the only force acting upwards here is the Rg force, the reaction to the ground. So now we're going to use F equals mu r. So we're going to have friction, which is 10g cot theta. And we're going to set that equal to mu, which is 0.75, times by 30g, the reaction force. So then what I'm going to do is I'm going to move everything onto the, I'm going to move the tan onto the right hand side, just like I did in the last question, and I'm going to divide by what I've got here. I can cancel out some tens, so I'm going to have 1 over 0.75 times by 3. So in this case here I'm going to have tan inverse of this thing here, so straight onto my calculator, tan inverse 1 over 0.75 times 3, and I'm going to get there pretty much 24 degrees exactly, 24.0 is my value for theta. So it's interesting to see that as we move the 10g force further down the slope, actually the angle of inclination actually reduces. Interesting. Okay, state how you have used the assumption that the wall is smooth in your calculation. There has been no friction force on the wall. So for this part C here, there has been no friction force on the wall. Okay then, thanks very much for watching. Have a go at plenty of the questions from exercise 7D. Make sure you have a go at these. There's lots of good questions in the textbook, and they generally follow a very similar format. You're taking moments for the resolved forces, equating left-hand forces to right-hand forces, equating upwards forces to downwards forces, and using the fact that F equals mu r in either one or both of the positions on the wall and the ground. Lovely, thanks very much for watching.